Alright, hey everyone, my name is Tyler. This is a presentation on state-of-the-art thread mapping strategies for NUMA multi-core systems. So let's go ahead and get started. This is the format I'm going to follow for the presentation. I'll start with some background information, then we'll talk about some performance concerns in NUMA systems, and then I'll explain two papers which have devised thread mapping strategies, and finally we'll look at their results. So NUMA stands for non-uniform memory access, and this is a memory access behavior that is present in some multi-core systems. One very important implication of non-uniform memory access is local memory access is faster than remote memory access. A NUMA system is made up of several nodes. Each node contains some computing resources, namely some processor cores, various levels of cache memory, and a memory controller, and data can be transferred between nodes through a high-speed interconnect. Now let's go ahead and look at some of the issues that NUMA systems face. One performance concern is resource contention. So resource contention occurs when multiple system components make a demand on a single resource. And this occurs with shared resources, and NUMA systems have a few shared resources. So each node contains a last level cache, or LLC, which can be shared with other nodes. We also have node interconnects, which connect nodes to one another, and these are obviously shared. The final shared resource is the memory controller. Each node has a memory controller that is shared with each processor core in the node. It's important to note that resource contention is a major source of performance loss. Alright, let's move on to locality. Locality refers to the fact that local memory accesses are faster than remote accesses, and this is because there's a greater distance between the processor core and the memory location. The remote accesses can also cause contention for node interconnects because the interconnects are used to reach the remote location, and too many remote memory accesses can be a cause of performance loss. Finally, we have memory congestion, which occurs when there's too much pressure on a memory controller. One intuition is to maximize locality at all costs, but this can actually increase memory congestion as the memory controller can become a bottleneck, so this can also be a cause of poor performance. Alright, so we're going to look at two papers and try and understand their thread mapping strategies and how they affect the concerns we just talked about. The first strategy is called Communication Aware and Memory Load Balance, or CMLB for short. CMLB's goal is to use thread mapping to improve locality while also avoiding memory congestion. The next strategy is Competition Aware Framework and Scheduling Algorithm, which I'm just going to abbreviate to CA. And the goal of CA is to use thread mapping to reduce resource contention in the system. Both of the proposed solutions are dynamic, so they have to try and approximate the system state. CMLB does this using COM Detective, which is a tool that's built using Linux's perf. But COM Detective builds a communication matrix that represents the communication between each thread in the system. And L3 cache misses are pulled to get an idea of a thread's memory load, and the memory load information ends up getting stored in an access load vector. CA uses a direct approach using the hardware's PMU, which is the performance monitoring unit. It basically interfaces directly with the hardware to provide information about various events. CA uses it to look at events associated with resource contention for the LLC, memory controller, and node interconnects. Next, the systems use the information they gathered about the system to inform a thread mapping policy. So CMLB has the communication matrix and the access load vector, which it uses to judge the system. First, all the threads are distributed across the system. Then thread groupings are determined using a greedy policy. The way this works is a thread group and a thread outside of the group, they both get looked at, and the communication matrix determines how much communication the thread is doing with the threads in the group. If it's a level of communication that's pretty high, then it becomes a candidate to join the thread group. But before it can join, first the access load vector determines if adding it to the group will break the memory load balance of the system. If the thread's able to join the group without breaking the memory load balance, then it's added. Otherwise, another thread is looked at instead. So basically, the communication matrix is used to maximize locality, while the access load vector ensures memory load balance is kept. Similarly, CA also uses system state to determine a mapping. It uses the metrics it gathered to determine nodes as hot or cold. Hot nodes are nodes that have high resource contention, and cold nodes just have low contention relative to hot nodes. The criteria for mapping is if a thread is in a hot node, then it needs to be mapped to a cold node. Otherwise, it's in a cold node and it can stay where it's at. So on to results. CMLB is tested against some other thread mapping strategies. Each thread gets tested under NPB, which stands for NASA Advanced Supercomputing Division Parallel Benchmark. Essentially, these are several benchmark applications that resemble a parallel application workload, and the results are examined for execution time improvement, QPI improvement, node imbalance, and latency. So you can see here we have 4 graphs. CMLB is represented by this blue color. Looking at execution time improvement, it actually slightly outperforms the other metrics across all the benchmarks. Next we have QPI improvement, which represents the node's interconnect performance, and we can see it's pretty consistent with other methods. In the lower left, we have the imbalance of memory bandwidth, and this is actually interesting as it shows CMLB is way more balanced than the other methods, and this illustrates how CMLB is successful in reducing memory congestion. Finally, there's application latency, and CMLB has less latency than the other methods. The CA strategy is tested against a system that doesn't use any kind of competition awareness, and the metrics that are looked at are the memory controller read times, QPI fetch queue length, and again, which indicates pressure on node interconnects, and we also look at LLC misses. In the top left, we have memory controller read times. The system that uses the competition awareness framework is in orange, and it can be seen that it has much faster read times, and this shows there's lower contention for the memory controller. Next, in the top right, we look at the number of LLC misses. This time the competition aware framework is in blue, and this shows it encounters far less LLC misses, meaning there's less contention for the LLC. Finally, we have the per node QPI fetch queue length. We're looking at the interconnect for 2 nodes in the system with and without the competition aware framework. And what's interesting here is the system that uses CA has less divergence across the nodes. So this shows the interconnect contention is more balanced instead of becoming a larger issue in just one node. So in conclusion, NUMA architectures are unique due to their memory access behavior. There's several aspects of NUMA which can affect performance. Locality, resource contention, and memory congestion can be addressed with thread mapping, which is shown by both of the proposed solutions as they're both successful. For future works, more of these thread mapping strategies could be considered, so their qualities can be better understood. Then a thread mapping policy for NUMA systems could be designed. Okay, that's all for the presentation. Thanks.